In today's video, we're going to walk through a Hooke's Law question. These are very common in GCSE physics and grade 10 physics. We're going to look at the direct proportion relationship between extension of a spring and the force, how that is represented on a graph, and then the questions they can ask around that. So make sure you have your calculator at hand, pen and paper ready to take notes, and let's go. Figure 3.1 shows part of the extension law graph for a spring. The spring obeys Hooke's law between A and B. On figure 3.1, complete the graph between A and B. So first of all, let's recap what Hooke's law is. Hooke's law states that the extension of a spring or some other material is directly proportional to the load applied up to the elastic limit. So between A and B, there will be a direct proportion relationship, which means when you double one quantity, the other one will double as well. So it will be a straight line. Make sure you use a ruler if you do this, if you come across a question like this in an exam. The name of point B is when something I described in my previous video, where it is the way to think about it is it's like the point of no return. So once you stretch the spring beyond that point, it will not return to its original size. In other words, you permanently damaged it. And it's known as the elastic limit, or sometimes known as the limit of proportionality. Okay. So at that point, when a small force is applied, you get a significant extension, and the spring will not return to its original size. Okay, so next bit, the average value of the load between A and B is 6 newtons. Calculate the work done in extending the spring from A to B. So we need the work done formula. So work done is equal to force applied times the distance moved. The force applied is always in newtons, and the distance moved is usually expressed in meters. So in this case, you can see the extension is being expressed in centimeters, so I will be turning it into meters. So the force applied is 6, and the distance is moved between A and B is, you can see that it's gone from 0 to 3 centimeters. So that is the distance that is moved. So it will be 6 times 0.03. So don't forget, I have turned centimeters into meters by dividing by 100, because there's 100 centimeters in 1 meter. And then that gives me an answer of 0.18 joules of work. Next part. The spring has an unstretched length of 4 centimeters. So that would be 0.04 meters. An object is hung on the spring, and the spring length increases from 4 to 6. Calculate the mass of the object. Okay, so we need to know the relationship between mass and weight, because they're not the same. So mass is measured in grams or kilograms, whereas an object has weight if it's subject to the force of gravity, and weight is always in newtons. Okay, so the relationship between weight and mass is weight equals mass times gravity, where for the purposes of this question, we'll take the force of gravity as being 10 newtons per kilogram. Hooke's law states that the extension of a spring is directly proportional to the force applied. So I can write this as an equation where x is the extension is equal to k times F. K is the spring constant, or the constant of proportionality, and F is the load. Remember, F is the independent variable, and then X, which is the extension, is the dependent. So if we double or change the value of F, then the value of X will be affected. Now, why do I need this equation? Well, in order to work out what the mass of this object is that has caused an extension of 4 to 6 centimeters, I need to work out K, because X is given to me as 2 centimeters. If I have K, then I can work out F, which is the force, and then I can turn that into a mass. So how can I get K? Well, if you look at the graph on the left, I can use the graph to help me work out the value of K. So rearranging gives me K equals X divided by F, and we can see an extension of 3 centimeters, or 0.03, is caused by a force of 12 newtons. So 0.03 divided by 12 gives me 0.0025. Right, so that is the spring constant. Now I can use that number along with the extension of 2 centimeters here to work out the force that causes this. Once I know the force, I can therefore get the mass. So using the equation again, X equals Kf. So therefore rearranged F equals X divided by K. The extension this time is 0.02. Remember, I've turned 2 centimeters into meters. The value of K is 0.0025, or in other words 2.5 times 10 to the negative 3. So putting that into the calculator gives me an answer of exactly 8 newtons. So the force is 8 newtons, or in other words, the weight is 8 newtons. Remember, weight is the same as force. They're both measured in newtons. So just for clarity, if I do this in blue, we know that the weight of the object is 8. M is the thing we're trying to find, and we know gravity is times 10. So you can see where this is going. To work out M, I just divide 8 divided by 10. So therefore 8 over 10 equals M, to give an answer of 0.8 kilograms. So that is the mass of the object that has caused an extension of 2 centimeters. Finally, number 2. The object is immersed in the liquid but remains suspended from the spring. The liquid exerts an upward force on the object and the length of the spring decreases to 5 centimeters. Calculate the upward force exerted on the object. Notice it says force, not mass. Okay, so this one isn't too difficult. So we know that a force of 8 newtons caused an extension of 2 centimeters. Because that's what it tells us there, just re-highlighted in blue. But now the liquid, imagine this is the liquid, and there's the spring, has sort of pushed the spring that way, and now the extension is only like 1 centimeter. So in other words, we got to find out what would cause an extension of 1 centimeter. So we can just use this to help us. If we know 8 newtons causes an extension of 2 centimeters, then half of that would just be 4 newtons. So therefore the upwards force must be 4 newtons. Right, so this I think is a more tricky Hooke's law question. It's more mathematical and involves a lot more thinking compared to the previous example. But hopefully now I've run through these 2 examples, you have a better idea of what to do should you get one of these in your GCSE physics or grade 10 exam paper, test, whatever it is. As always, if you have any questions, please comment down below and I will endeavour to get back to you. Otherwise, like and subscribe, and I will see you in the next one.